The subjects we are going to see today are linear programming and simplex method. So what is linear programming? Let's start by seeing this. Linear programming is one of the widely used ways to perform optimization. It helps you solve some very complex optimization problems by making a few simple assumptions. We are going to see what linear programming is, its basic terminologies, and the process to define a linear programming problem, solve linear programming problem by graphical method, and also by using simplex method. So again, today we are going to see how to solve some problems that you did not know how to solve before. This is an example of a linear programming problem. Let's say there is a FedEx delivery man and he has 6 packages to deliver in a day, and the warehouse is located at point A, and the delivery destinations are given by U, V, W, X, Y, and Z. And these show the distances between the delivery locations. The figures, the numerals there show the distances between the delivery locations. To save fuel and time, the delivery man wants to take the shortest route. Which of these, which way should it go so that the total distance the delivery man travels is going to be minimum? This is a linear programming problem, for instance. Now, we had mentioned that a linear programming problem is the type of problem where there is an objective function which can be shown in linear form. So that's where its name is coming from. A simple one is an objective function which is shown by this simple linear equation. It's a function of 2 variables, x and y, and it is expressed as 4x plus 3y. And we are asked to maximize under the constraints. The 2x plus 4y is less than or equal to 220. 3x plus 2y is less than or equal to 150. So these are the constraints. The constraints are expressed in terms of inequalities here, but the inequalities are less than or equal to 4. And the variables are larger than or equal to 0. That means the variables are positive. The objective function is in linear form, linear function, and the constraints are expressed as less than or equal to 4. Now, what happens if I did not have these rules? What happens, for instance, if the objective function was not a positive linear function, or if the inequalities or one of the inequalities was larger than a certain number? Then, as you know, you can change this sign less than or equal to or larger than or equal to by multiplying by -1. Also, you can change this if this is a negative function by multiplying it by -1. That is, maximizing something is also equal to minimizing it is negative. So we can form the other problems by easily multiplying by -1 to this form. Also, the variables we set must be positive variables. If they are negative, we can create new variables by multiplying by -1. So this is not a limitation saying that the constraints must come this way and the objective function must be a positive function or the variables must be positive. They do not come as a constraint, as a limitation of the solution capability of the problem, because other types of problem can also be converted into this form by simply multiplying by -1. Now, you can see from these graphics, we are going to solve the problem first by using graphical methods. You can see by these graphics why we have these rules, why we have to have the variables larger than or equal to 0, because then if I look at the graphics, we are confined to this region where the variables are positive. Otherwise, you would have to cover the entire graphics, entire two-dimensional graphics, because we have just started to learn these techniques. We are now confining ourselves to two-dimensional problems. That's why we have a performance criterion expressed in two variables. So it's going to be a two-dimensional problem. So we can visualize it easily here, and making the variables positive, confining them to positive values, means that the region we concentrate in is now a more limited region. Instead of looking the entire 4 quadrants, we are just concentrated on one of the quadrants where the variables are positive. Also, if I make the inequalities less than or equal to, still the region, admissible region, I am going to concentrate on is going to be more limited. Because I do not want to deal with infinitely large regions. So this admissible region is limited. It has got no boundaries. It has been limited by the vertical axis, horizontal axis, and these inequality, if I make them equal to 0, these give me two lines. One is 3x plus 2y minus 150 is equal to 0, which is this line, and 2x plus 4y minus 220 is this line. Okay, so because of the inequality less than, I look only this region, which is a finite region. If it were otherwise, I would have to deal with an infinite region. Of course, when the region, the admissible region, is an infinite region, I cannot talk about maximizing or minimizing it because it is infinite. That's the reason we have to make these assumptions at the beginning, that these variables must be larger than or equal to 0. So we confine ourselves to this part of the coordinate axis plane. So it is in 2 dimensions, but in general, this is applicable to n dimensions. And the admissible region is a convex region. So we are now concentrated on a two-dimensional convex region. What you remember, what is a convex? The convex is that if I draw any line between any 2 points, it stays inside the region. This is convex. The outside region is a concave region, because if I draw 2 points on the boundary, it may remain outside the region. So this makes it the outside region concave, whereas the admissible region, which is the inside region, it is convex, because if I try to join any 2 points inside the region or on the boundary of the region, it always stays in the region. So this is called, since it is two-dimensional, it is called convex polygon. If it were, for instance, three-dimensional, it would be a polyhedron. In general, this type of n-dimensional regions are called polytype. Okay, so we've got polytype, polygon, and polyhedron. And in this course, we are interested in polygon type, convex polygon type of admissible regions, like we see here. So, while finding this feasible region, now we have a picture of the possible solutions of a problem. The goal is to maximize objective function. Of course, we are now talking about maximizing, but we have seen that it is equivalent to minimizing the negative of this. So this is our objective function. Pxy is equal to 4x plus 3y, and our goal is to maximize it under the constraints. There are always, in life, there are always constraints. If there were no constraints, we would be able to maximize it. I mean, by using infinitely large x and y values, but this is not the reality of the life. In life, there are always constraints. So let's say this is our optimal form. I mean, if I find the optimal x and y values, which is going to maximize it under the given constraints, we know from the previous lectures that if we put star on the variable, that means it has got the optimal value. So if we solve this for y, we make y is equal to p over 3 minus 4 over 3x. Okay, so we make it like this. So here, what happens if I want to maximize p? What happens? So this is an equation of a line, y versus x. So it's going to be a line on the xy plane. If I maximize p, if I want to maximize p, what happens? It gives an equation of a line, and whatever point in the feasible region passes through this line is the optimal solution. The y-intercept of this line is p over 3. As p is maximized, this intercept should be maximized. So we look at a number of lines, we draw a number of lines with a slope of -4/3, and we look at the y-intercepts, and the one with the largest y-intercept is going to be the optimal solution, because the largest y-intercept means largest p/3, and it means largest p, and this is what we are looking for. This is what I mean. So we draw several lines with slope -4/3, and the y-intercept is where they cross the y-axis, or x is equal to 0 axis. Okay. So if you look at these, you can see that this line which goes through this corner has got the largest intercept. So does this correspond to our optimal solution? Very probably it does. So we may write a rule from here. The rule is that the optimal solution lies in one of the corners. So I have a polygon, convex polygon. The convex polygon in this case, since I have got two boundaries coming from the coordinate axis, and additional two boundaries coming from the constraints. Since I have got 4 constraints here, I have got a polygon with 4 corners. So the solution is going to be lie on one of these corners. So graphically, I can see here that the lines with this slope which go from these corners, okay, so these 3 lines, 3 corners here, okay, and you can see the one here is the line with the largest y-intercept, so this should be the optimal solution. Let's look closer to this now. By looking at this graph, we can see that this should be the optimal solution, since it gives the largest y-intercept. And the fundamental theorem of linear programming here is that the optimal solution lies in one of the vertices of the polygon of the admissible region. And this is, of course, for 2-dimensional problems, but in this course, we are confined to the 2-dimensional problems. Okay, and plane eye view shows that this should be the optimal solution, but let's check it, let's verify it. Now, which of these vertices, A, B, C, D, correspond to the optimal solution? Remember that we are trying to maximize this function here. Obviously, we can eliminate A because at this point, it is 0, because X and Y are all 0, and this is 0. So we have got 3 candidates, and B, C, or D are our candidates. Which vertex gives the optimal solution? We had drawn these lines with slope of -4/3 and looked at the lines which are going through these vertices, and we checked that the one going through the C vertex has got the largest y-intercept. So this should be the C, should be the point which gives us the optimal solution. Okay. Can we also verify this by calculation? So this is the written form of the explanation I had given to you orally. The line that maximizes the y-intercept is the one that passes through C, and therefore, what does this correspond to? And what are the coordinates of C then? I mean, if I find the coordinates of C, determine the coordinates of C, then this is going to give me the solution for X and Y, which is going to maximize P. Okay, but look at this. Can you give me an answer how we can find these X and Y values now? Just think about it. Now we have, from the graphics, from the graphical method, we have figured out that C is the vertex of the polygon, which gives me the optimal solution. What I mean by the optimal solution? The solution which maximizes P. So what remains is to find the X and Y values at C. How can I find this? Does anybody have a clue about the solution? So it lies on the boundary conditions, the solution, because the boundary conditions gave me two lines. And see that this point, the optimal solution, lies at the intersection of these two lines. Therefore, it should satisfy both of these line equations. Okay, how many unknowns do I have? I need to find the X and Y at this point. So I've got two unknowns, but I have also got two equations. The equations are the equations of these lines. So I can write two equations and solve them for two unknowns. This is a trivial problem. Therefore, from here, I can now go ahead and figure out the X and Y values, which is actually going to maximize the P. Okay. So C is at the intersection of these two lines. 3x plus 2y is equal to 150. And 2x plus 4y is equal to 220. So my solutions should satisfy both of these equations. Two linear equations in two unknowns. I, of course, know this is a bicycle problem and how to solve these equations easily. And when we solve these equations, simultaneous equations for two unknowns, we can find the values which is going to optimize the values of, or the coordinates of C, which is 20, and x is equal to 20, and y is equal to 45. Of course, I put stars on these values because they are the optimal values. And when I put them into the equation, this gives me 250. And let's check. Let's make sure that it is actually the optimal solution. And if I put the coordinates, we said that if this is a fundamental property, the optimal solution lies on one of the vertices. And let us check the vertices, each of the vertices. If I cannot do anything else, I can check the vertices and see if each of them give the optimal value. And at vertex A, it is xy is 0, 0, gives p is found as 0. At B, 50, 0, p is found as 200. At C, we had found C as 215, and D actually 165. And we see from here, in fact, that C gives us also the optimal value. Of course, for the polygon, this is not too difficult to find, but if it becomes a polytope, polyhedron, for instance, or a larger dimensional linear programming problem, then it becomes very difficult to do it like this. So there may be many vertices to check by simple calculation. And if I want to do it by hand, so this method is a rather handy method, and it gives me an insight how the linear programming methods problems are solved. So we started by the simplest case, which is the two-dimensional, and it allowed us to see the problem and use the graphics to solve the problem. Of course, when the dimensions and the number of variables increase, the technique is applicable, but the seeing it as easily as this one is not possible. And can we minimize now this function under these constraints? Okay, do you see any difference between this problem and the previous one? Does anybody see any difference? In the previous example, we had the maximization problem. Here we have a minimization problem. And there's one more difference. The number of constraints in the previous one was only 2. Of course, we had the constraints also these. So we were bounded by the coordinate axis and by two lines which correspond to two constraints, whereas here we are bounded by a third condition. Okay, so these are the basic differences. So if you put in these all into graphics, what sort of a thing do we see? Okay, now in the previous case we were bounded by these two coordinate lines, but now because we have a third constraint here, which is this one, the C plus W is less than or equal to 7, and so this gives me a more constrained region like this one. Constraints increased, the number of vertices also increases, as you see. In the previous case, we had only 4 vertices. Here we have got 5 vertices. So these are the basic differences between the two problems, but the solution method is going to be the same. Again, we are going to utilize the fact that the solution is going to be on one of the vertices of this polygon. But now, if I drove the lines of my objective function, and if I look at the lines which go through the vertices, this time I'm looking for the line with the minimum y-intercept, because this time I am looking for the solution which is going to minimize. This is the equation function that I want to minimize. So I put them into this form, getting W to the left. And now we already know from the fundamental theorem that the solution is at one of the vertices of the admissible region, which coincides with this function. And if you look at these red lines, the line which goes through the A is the one with the minimum y-intercept. So if we determine the coordinates of the A point here, that means we are going to find the solution, which is in terms of x and y, which is going to minimize this function this time. And we already know how to find this solution. It is going to be, I'm going to write two equations, one for this line and the other one is for this line, and one for this, the other one is for this, or let me just change my cursor. Okay. So two equations, one for this line and the other one is for this line, and the point here satisfies both of these line equations. So again, it gives me two equations for two unknowns, and I solve. So these lines are given by these two equations. And if I solve them for the variables c and w, in this case, instead of x and y, we use c and w. C is the horizontal line, w is the vertical line. And we can easily solve these two equations for these two unknowns and find the values. And the values of C is 3.411, which is here 3.411, and W 0.59 here, okay? And when we put them into the equation that we want to minimize, we obtain this value 2.29. Okay. Here also we saw that the solution was on the vertex of the admissible region, and this is true for all linear programming problems. So we can state the theorem now as, given a convex polygonal admissible region and a linear objective function, the solution that maximizes or minimizes the objective function will be located on one of the vertices of the admissible region. Now, let the objective function be this. And let the maximum value of this function be p. And let the minimum value of this function be q. Okay. In each case, I can write the equation in terms of y as this. If I am trying to maximize, I am going to look for the line which goes through one of the vertices with the maximum intercept value. For the minimization case, this time I am going to look for the line with the minimum y-intercept value. If I show this graphically, the fundamental theorem says it's going to be on one of the vertices of this polygon. And if I am trying to maximize it, then I'm going to look for the line which passes from one of these vertices with the maximum y-intercept value. In this case, it is this one for the maximum solution. And for the minimum solution, I'm going to look for the minimum y-intercept value, and it is this. And I hope it is clear for you all. This graphical solution is very handy. And make sure that you go through these examples.